All right, good, cool. So,
Instead of looking at that, look over this.
yeah, sure. Careful, careful. Good. All right, let people settle down for a bit and then start. Yes. All right, cool. So, hi. Here, everybody seems to be talking about AI these days. There's not like a single place that you could go where you can escape the discussion of AI. Unfortunately, you have to bear with me for another few more minutes where I talk about AI. So, we have been playing around with machine learning models for a bit, especially after GPT-2 came out. But before ChatGPT came out, we were like really excited about it, and we were trying to build like lyric generation bot and all that kind of stuff. No one really cared about it until ChatGPT came out, and world seems to have collectively lost its mind on this thing, which is very exciting, like for people like me. So we built a podcast player. So, but before that, a bit about me. My name is Vagni. I've been writing code, or people have been paying me to write code since 2001, actually. I love building software, and even better, I love building great teams, actually. And I still code daily. So I mostly do work with Rust, Go, TypeScript, Python, and I try to build like cool little applications. Um, so I moved to Canada about 5 years back. Actually, I was in India, if you can't already say. And both my kids, one is 10, the other one is 6, they're studying French immersion. I don't speak a word of French, and they've already started conversing between them in French. So that's a problem for me as a dad. So I wanted to build an app that will let me learn French. So I started actually doing like French learning books, like parallel textbooks sort of thing, where you have both English and French at the same time. But I found, I wanted a better way to learn this. And so I was looking for a podcast player which would also have these parallel subtitles. There was like a couple of Chrome extensions that let you watch like Netflix with parallel subtitles and stuff like that. But video is very distracting. I wanted to have like a textbook or an audio experience. And so we built Kili. So let me give you a quick demo, and then we go from there. So live demos are always hard.
Mais on peut se demander quelle est l'utilité réelle de l'intelligence artificielle. Est-ce que toutes ces inventions sont seulement des gadgets ou est-ce qu'elles représentent de vrais progrès? Selon une étude réalisée en 2020,
So, as you can see, I don't want to bore you any further on this, but as you can see, this actually, not only lets me enjoy content in like native speakers kind of language, it helps me see the language, like the French language, and also seeing the translation in English. And it's not all, it's not in English, it's in Spanish, but then you can also change it to English, and it would work just as well. So, like for example, here, it basically talks about this. Let me play this. So it's from the same podcast, but I
ne parle pas d'un scénario de fin du monde comme dans les films de science-fiction, mais des inquiétudes quant à l'impact de l'intelligence artificielle sur l'emploi et notre place en tant qu'humain dans la société.
So yeah, and that brings us to the point of this talk. We just wanted to figure out, okay, this would definitely have an impact because, this is the work of so many more people transcribing videos, translating videos, and doing all this. So I want to share how we built it and kind of the lessons we learned along the way. So let me go back to slideshow mode. So the obligatory XKCD slide. I don't know if you've seen XKCD. He's like a really famous comic artist. And and most people's machine learning systems are like this, right? You just put a whole bunch of data, and then you use a whole bunch of linear algebra on it, and then you stir it enough until you get the results that you want. And if you don't get the results that you want, you either apply more data or you apply more linear algebra, right? And that was the state of machine learning for a while. From our experience, it's kind of gotten better, but this is our architecture. that we have for Kili. So most of the app is written in Go. By the way, this is not an app that I built. When I say I, so it's basically I mean, Jahangir is here. He contributed quite a bit. So that's that guy there. And then there's Kalpesh and there's Madhava who helped us deploy. So it's definitely a team effort. But the pain was mine in terms of like learning podcasts and things like that. So I somehow roped these guys into my personal pet project. So the app is mostly written in Go. And what it does is like it stores these podcast metadata in Postgres, and then we kind of query it and poll it, and then we download the data, and then we store it onto S3. So these are just the MP3 files, the podcast metadata that comes from it, like the image on the podcast, the title, and so on and so forth. And then we have written a component called the transcriber, which mostly uses OpenAI Whisper, but then we also have a little bit of our special sauce on it in terms of how we tokenize sentences and so on and so forth. And then we take all this data and then we store it in a vector database. So we'll talk a little bit about what a vector database is and what we exactly store, but we actually store multilingual embeddings. If you notice when I searched in English, and it actually gave me the results back in the native language that the podcast was in, actually, right? And part of the magic is because we use a vector store, and we don't use like traditional sort of like an open Elasticsearch or like an open search sort of a query. It would never work, right, with that. And then we use another model for translation. It's called FLAN-T5. A lot of people talk about GPT and this thing. I believe FLAN-T5 is the most underrated model of all. It's extremely versatile. It's by Google. It's very liberally licensed, and we found that great for translation. Not just for translation, you can use FLAN-T5 for a whole bunch of other things. We'll talk a little bit about FLAN-T5 as well. For translation, we're using FLAN-T5. We then store all the translated parts back into S3. So you have these, and what we store is basically like the start of a sentence in terms of the timestamp, and then the actual sentence in whatever language that is. So if it's an original, we store it in French, and then we have a similar sort of format for the translated language. And we then expose the whole thing through an API, and that is read by Next.js. And the API is also written in Go, and the UI is written in Next.js. We use, only for the search, we use Python. For search and for the machine learning operations, we use Python. And the reason we use search in Python is that we actually use a sentence transformer model there, which allows us to compute the embedding when we do a search on this. So we'll talk more about most of these models and then where they are situated. So almost all of this value has been unlocked by this transformer architecture. It's called, it came in the paper called Attention is All You Need, and it's called the transformer architecture. And this architecture has basically given rise to whatever we are seeing today, right, in terms of machine learning improvements. Earlier, there used to be NLP researchers, vision researchers, audio researchers, and so on and so forth. Machine learning used to be split across different fields. But now with transformers, it's the same model architecture that's driving Stable Diffusion and DALI and Midjourney and 11 Labs with audio and GPT and BERT, and pretty much it's the same model, right? There's very little difference among these models, mostly in terms of data or in terms of how they tokenize and this thing. But the fundamental architecture of these models is pretty much this. So it starts with, so there are two parts to this model. On the left, you have the encoder. They call it the encoder of the transformer. On the right, you have the decoder of the transformer. So what you get is you have various inputs, and inputs is very loose here term, because you could have a waveform as an input. You could have image like description as text as an input, or just or you could have actual text with labels as an input. It doesn't matter, right? As long as you can turn them into numbers, right, and pass it to it, and there is some pattern to it, that's basically the input. So essentially, input is like a huge vector of numbers that you pass in, and then you have this really cool thing called the multi-headed attention layer, and that is the core of all these transformers. So what multi-headed attention gives is that, say for example, earlier when you used to do neural network, NLP, natural language processing, you would basically try to do things like term frequency, inverse document frequency kind of thing, where you say, oh, if you want to find how important a certain word is in a document, you basically count all the occurrences of the word and find out all the words in the document. And if this word has occurred more times in a document than this thing, right, compared to some other word, then this word is more important in this document. But then if you have a document like spam, 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 then it's completely nonsensical, right? So it started from there, information retrieval for ranking and things like that. And then people wanted to find out, hey, there is a relationship between words and we needed to build this relationship between words. And that basically became, they had this concept of word embeddings. And there were like very popular models like Glove was a word embedding model, where they basically decided to make each word a static representation of numbers. Say there was king and queen, each would have a certain set of words, and then there'd be man and woman, they would also have their own set of numbers, and say they would map it on to say 128 dimensional space or something like that. And then they would say, roughly speaking, king minus queen plus man should give you woman, right? So in terms of this like mathematical relationship, they tried to come up with these kind of static relationship kind of words, and they used to train these models, and they used to put it out in the open. And that was very popular. A lot of people used Glove embeddings. I had also used them in the past. And the problem with Glove embeddings is that, say when you say something like a bank, right? A bank could mean a bank that you could go to withdraw money, or it could be a river bank, right? So words often have different meanings, and so you couldn't represent a word just by a set of numbers, because what those numbers should be the function of what comes before and after it, actually, right? The words that come before and after it. And that is what multi-headed attention actually solved, right? Multi-headed attention was a way to computationally say that, hey, this word actually depends on the context of the words that are around it, and it actually gave a mathematical representation of how to come up with this by just throwing lots of data at it and let it figure out where it is. So that's essentially what the transformer allowed people to do. In fact, the first paper was on machine translation. Attention is all you need was like the first application of this was on machine translation, and the researchers found that it was absolutely groundbreaking. This approach that they took to machine translation basically beat all the other machine translation work that people had been doing, and they didn't have to do any specific language level rules. It was just generic math that just worked out of the box. So, and if you see, and then there's this encoder and the decoder box, but as you progressively see, other models also follow the same way. So this is the Whisper model. So Whisper is the model that we used for speech recognition. So when we played an audio, it would take the audio and then give us back text. So this is the Whisper model. And initially, this is the input that you see here at the bottom. This is what is going as the input, which is the waveform of the file. So usually our blog posts that we transcribe are like a 30-minute blog post, but you can't pass in 30 minutes of data. So you pass in 30 seconds of data, and then for every 30 seconds, basically this input sequence would run. So what it would do is it will take the waveform of the data, and then, and when I say waveform, it's like very simple mono waveform, and it says, oh, this amplitude is this value, right? So it basically normalizes on the amplitude and say, the louder it is, it basically gives a number to it. That is it, right? It's like really dumb sort of an encoding here. And then it basically goes through this bunch of these encoder blocks. So as we saw here, you have the NX, which is here, which basically means number of heads that they have. So they used 32 heads on the encoder block. So you had 32 times this would repeat. And then in the bottom, they would basically give it a task. So this would be like start of transcription or start of translation, which language the original audio was in, what kind of job that you would do, because Whisper could do both. It could either transcribe it or translate it. Even though Whisper could do translation, we found it wasn't that great, so we are just using it for the transcription tasks. And then you can give it some prompt, right? And we had to use a little bit of prompt engineering in Whisper as well, because when we are especially doing French text, it would completely miss all the punctuations. It would miss the full stops and the apostrophes and the commas and things like that. It just used to be like a huge wall of text, and it was very difficult for us to figure out when did this sentence end. So we used to basically put in like an example of this, like welcome to our podcast, and then we put in like full stop, we're glad to have you here, exclamation mark, and things like that, basically to tell the decoder block that, hey, it's okay for you to produce punctuations, like to things like that. And then it would basically give out these next token predictions and so on and so forth. I mean, I don't want to get into too much details over here, but the idea was that, they had different ways in which they were training it. They were either training it to produce transcriptions or translations, and they used to give it in this format. And the cool part about this, if you have some low resource languages that are there, say for example, there is a language that doesn't have enough speakers, especially, I mean, like the local languages here, or even back in India, there are a few languages which have very, very low resource languages where there aren't a lot of speakers. This model basically can be trained on any of those languages. So it doesn't matter whether it's English or Russian or Meithei or whatever it is. You can basically train it on any of these languages. And once we used this, we then used, sentence transformers for generating embedding. But to generate sentence transformers, you first have to understand BERT, actually. So BERT stood for bidirectional encoder representation of text. And this was a model by Google, and what they did was they basically used to take a word like I am going to college or something like that, and they would shoot words in between. They'd just say I am dash to college, right? Something like that, right? And then they would shoot words in between, and they would train the model to predict the right word. And Google basically trained it on a whole bunch of text because Google had basically crawled a big corpus of text. And so they basically trained it on a whole bunch of text, and they just generated like a base model. And all it did was it would predict the next word, right? Or it would predict the missing words given that you had masked some words in between, or you had shot down some words in those sentences and you presented an incomplete sentence in that. And then they basically used that model, that huge pre-trained model, and then they fine-tuned it on different tasks. And that's the concept of fine-tuning, is that you take this pre-trained model, which was very expensive to train, and then you would train it on your task, which is very, very specific. So in the paper that they had examples of 3 different trainings. One was machine natural language inferences, which basically said if there are 2 sentences, they basically said, is this sentence contradictory to this sentence, or is this sentence in agreement to the sentence, or is this sentence neutral to the sentence? Right? They would train it on that. They trained it on NER, which is named entity recognition, which said, hey, is this a name or a place? Or is it an animal? Is it like a famous person or something like that? They used to identify those entities in those sentences. And then they had SQUAD, which was Stanford question and answer data sets. So they used to do this. And this, for the longest time, was state of the art. I mean, when I say longest time, 2018 to 2022 was like the state of the art, right? But it was still pretty amazing because with BERT, there was a whole bunch of startups pretty much in the legal space, right? Lawyers, a lot of legal tech firms basically looked at BERT and they said like, hey, this is pretty much what all our lawyers do, right? We're going to train models that will allow us to search better on our legal documents using BERT, actually, right? So it did a whole bunch of these things. And the way they did this was through, this is this paper that came out called SBERT, or Siamese BERT. So they basically trained 2 different BERT models as Siamese twins, actually, and then they gave it 2 different sentences. Say, for example, they would be like, hey, I'm giving a talk at a conference, and versus there was a talk that was handled by this person at the conference. They're very similar sentences, actually. So what they used to do is try to get these 2 similar sentence pairs and then trained 2 parallel networks on it, right, or side by side. And they basically said, hey, make sure that when you generate the outputs out of this, they are as close as possible. And when I say as close as possible, they tried to do a cosine distance. So the cosine distance essentially means is that, so all these embeddings that are coming out are in a higher dimensional space, something like a 512 dimensional space. So they basically wanted to train it in such a way that the angle between those two 512 dimension points, like from the origin, is as close as possible. I know our brain hurts just thinking about 512 dimensions, but then I've been doing machine learning so long that okay, there is a math there that gives us there. I just agree that there is a 512 dimensional space. In math, anything is possible, right? So we have to accept that. And then the researchers basically looked at it and they said, cool, that's great that we can do sentence similarity between two sentences, but can we do this for multilingual sentences? So what they did was they had this teacher model, which was a BERT model that they had already trained on the sentence vector, so that will give us the sentence vector implementation. And they had a student model where they passed in these translated sentences. So here you have an English sentence, hello world, and a German sentence, hello Welt, and then they would pass both of these to these models, and they basically decided to turn this so that it will produce a similar enough vector representation for hello Welt as the same as hello world in English, right? And the MSE loss is basically mean square error. It's just a statistical term that people use to get the square of the errors and then do an average of the square of the errors and then try to minimize that. So that way it kind of like make sure that the standard deviation isn't lost. So that's, so they did this. And this is the core of our, the way we are able to do sentence structures. So I showed you in our, this thing, so we have the transcriber, which actually used Whisper, and then we use, sorry, I was pointing on the screen. So you can't see my finger, can you? So you have transcriber, which uses Whisper, and then we had the sentence transformers, which then used, the whole BERT mechanism to actually generate these embeddings, actually, for us, so that when we take a sentence and then turn it into vector embeddings, regardless of which language you would search it in, the vector embeddings would be, same. And then we push it down to a vector database. And this is the vector database that we use. This is called Quadrant. And what Quadrant enables you to do is, unlike a typical database which stores rows and columns and metadata, things like that, this also stores metadata, but it's primarily used to store these higher dimensional vector numbers, right? And it knows how to calculate the similarity between these numbers, given there is a whole bunch of them, large scale, right? Imagine if you take the entire corpus of the internet and you feed it through these vector machines and store all of them as vectors, and you basically want to say, I search for impact of AI on society, and it needs to quickly find all the related documents that are close to my space, right, to that. So, and this is what it does. So it implements an algorithm called HNSW, or it is called Hierarchical Navigable Small Worlds. And the reason it's hierarchical is that it basically converts these points into this massive connection spaces, and then tries to find out a node that has the most number of connections, like a few sets of this, and it'll keep it in the next layer. Then it will basically go down to the next layer level and then add more nodes here, which have more number of connections, and so on and so forth. So if you're looking for, say, the red dot that you want to find, it tries to find out, hey, what's the closest dot to the red dot, and then it goes there, and it goes down, and it says, hey, this dot is closest to the red dot, so I'm going to go down here and go down one level, and it says, hey, I found this to be the closest one for what you're looking for, and it gives me that green dot as a result, actually. And this is, of course, showing it in like two-dimensional space, but I mean, most of these are like in n-dimensional. So you could choose, depending on the embedding size that you use, it could be 512, 768, I think OpenAI's ChatGPT gives like 1536 dimensional space. So it depends on where it is, and it actually finds that really, really quickly. And that's the point. And this whole vector database space is like exploding. I mean, we are using Quadrant. We also evaluated Milvus. I think Jahangir evaluated Milvus for a little bit, and he still is a fan of Milvus. I'm a fan of Quadrant. I use Quadrant. And then there's also VV8, Pinecone. There's a bunch of things. And I mean, most of the existing like open source databases have also started implementing HNSW indexes. So you might start seeing that in Postgres. You might start seeing that in Elasticsearch. I think Elasticsearch already supports HNSW indexes. So you do this. But this is more like a specialized vector store that we use. And finally, we come to the translation bit. So Google again wrote, I mean, Google did BERT, but then they also did TFI. And TFI is a paper that they said it's like a text-to-text transfer transformer. I know there's a whole bunch of T's on that, right? I mean, so why would you put so many T's in one model, right? So, but the idea was that, hey, we use BERT. BERT was used to then, break it down into like different models. Like you had different, one for like question and answer answering, one for just doing like sentence transformers, one for these things and so on and so forth. They said like, can we turn one model that can do all these tasks, right? So, and we basically say each task is basically a string earlier, and that's like this thing. So each model essentially would be like this thing. So Cola would basically say, hey, is this sentence grammatically correct? Is it an acceptable quality of a sentence? Or translate English to German would be like, oh, this is a translation task to do that. Or STSB, sentence 1, sentence 2 would be like, STSB is like similarity between these sentences, sentence similarity. And then it would be like, oh, rhino grazed on the grass and rhino is grazing in the field. Are these similar, right? Or how similar are they? Or do summarization. So they try to basically map multiple tasks onto the same model. And what they found was if you feed it enough data, it actually works very well, right? And a similar model can do multiple tasks. In fact, I have one model on Hugging Face which does grammar error corrections because I wanted to get more into this field and try to do this. So I decided to, have the most impactful AI tool that I've used so far is Grammarly, and I wanted to recreate Grammarly. So I basically ran a model on TFI to fine-tune it for grammar error correction, and it worked quite well. And then they went ahead and they said, hey, this is good, TFI is good, but what if we fine-tune it on instructions? So an instruction fine-tuning is the same thing that GPT-3 became ChatGPT because of instruction fine-tuning, right? So they had this paper called InstructGPT, and then they turned it into RLHF, which is real reinforcement learning with human feedback on this. But the idea is the same. The idea is that you take this massive pre-trained model that they have, which does all these things, and then you give it instructions and give it examples of that, and then have that produce the right kind of output. Now, for our case, we could have used TFI. In fact, we tried using TFI earlier. The first model that I tried was TFI, because when I search on Hugging Face on translation, TFI just comes up there. And I tried using TFI, but I found the translations weren't that great. And when I started using FLAN TFI, right, the translations are much better, even though translation was a very, very small subset on which FLAN TFI was trained. But there is something about emergent property about this model is that when a model is trained on some other task, it automatically gets better at a task that it was not trained for, which is totally bizarre if you think about it. It's not generally how a model should work, because the more you fine-tune on a particular model, it should fine-tune for the task and not for this. But in this particular case, I found FLAN TFI was a much better model for our translations on this, and it was just empirical. This thing. When I say empirical, it's like I looked at the translation, I did it, put it on Google Translate. It wasn't quite the same, and so right, and also doing this. So and I found FLAN TFI was closer to that model, and I was also learning French to a certain extent that I could say, if I could detect bad English translations, I'm pretty sure like most other people could do as well. So that's there, and that was a part of the pipeline, and these are the learnings that we had, and these are the models that we used. And again, all this is running on Amazon, on AWS. We did not use, and our goal was never to use like a hosted API and to do it ourselves. Although, there are hosted APIs. There is Google Translate API. There are APIs which do transcription, things like that. The idea was that, okay, we wanted to run it on our own, like sort of like a machine learning GPU workloads and see how that works. And all of this was running on a G5 2x large on Amazon, which is the cheapest GPU instance that could run all of this, actually. So it is not the cheapest GPU instance, but it was the cheapest GPU instance that could run all of this. So we essentially did our work on that. Yeah, and if you have any questions, I'd be happy to take them. Oh, Kili. Yeah, Kili stands for a parrot. So it's the word Kili basically means parrot in Tamil. And the reason was that I was looking for polyglot, Polly the parrot, and so Kili. Yeah. Yes, please.
Just a small question, like, this T5 is only for the languages, or you can also use it for images as well?
Any images? No. T5 is only for languages. Yeah. T5 is only for languages at this point. That's yes, please. Yeah.
I don't know if you can tell this, but do you have an estimate of how much did it cost to run this in AWS?
Oh yeah. Yeah. So right now, I mean, like if you see here, for people to use it, right? We don't have anything in the machine learning hot pipeline. So we don't have anything like this. I mean, including our experiments where we were goofing around and doing things with this thing, it cost about like $2,000 to set the whole thing up, like in terms of AWS like billing cost. But that said, it's only the transcription and the translation that needs to run through the GPU. So we could batch up these things. Like it could, you could do it like once in a month for a couple of hours or something like that, and you're good, right? Because podcasts aren't that frequent, and the idea is that these are curated podcasts. It's not meant to replace an actual podcast listening app.
Right, so in the end, the life queries are very simple. So to say, you don't need the GPU for that.
Exactly.
You just need to have everything stored.
Exactly.
But basically, all the training and your learning,
yes,
feeding with models and everything, all in is just $2,000.
That's right.
What was that time you took for this?
2 months, 3 months. Yeah, 3 months. Yeah. Yes.
Can you, I mean, is it possible to write a model that can do programmable actions also, or do you need additional layer?
Oh yeah, I mean you can. So again, like I said, right, most of these models are just doing next token or next this thing predictions. So you can pretty much make your model do output whatever. So one of the things that it can output is basically to say what function in which language should I call, right? So and that could be and that could be the output. And so this, in fact, we are doing one demo, and I'm hoping that we can actually demonstrate that as well. We are actually building a chatbot which connects to internal APIs, which will then like make these calls, but within an auth boundary. So the LLM is just there to instruct on which calls you need to make. So there is this thing, but then it uses the auth API, or API behind the auth layer to actually get those results.
And with that, we can also, I think that answers the question, but just want to confirm that we can also define what kind of output that we want.
Absolutely. And you can also, and this is still all using ChatGPT API and things like that. You can prompt your ChatGPT API to make sure that it doesn't answer anything apart from whatever is in the domain of what you are asking for.
One more question. How, one of the things that with the ChatGPT, right, some of the bigger organizations, they are making the employees stay away from it because it's more open.
Right.
It's there, it's just going out on the web, right? So,
right.
Will there be any security implications? I mean, how would that work if you are writing your own private model that is working within your own organization?
That's true. So two things, right? I think initially ChatGPT was collecting all the data, right? That's there. But starting March 2023, they changed their privacy policy because they were basically looking to commercialize their API. And so they don't collect any data that comes through API requests. If you are registered as a business on ChatGPT. So when you create an API key and you say, I'm doing this for business, they don't collect data on that. But for everything else, basically they slurp it in. That said, there is also Azure OpenAI service. There they don't collect any data. That's for ChatGPT, right? ChatGPT and OpenAI. There's also Claude, which is more business friendly, but then they don't have an open API. You have to basically contact their sales team and get that. So it's definitely meant for like more like involved customers. But apart from that, I think Llama 2 is going to be a huge game changer because Llama 2 is a much smaller model and it can run on a single GPU when you quantize it down, and that can be fine-tuned for your like customer needs, right? That we have, and I think that's something that I am exploring as well, and hopefully be able to talk about like once I get more info. Yes.
So between Flan T5 and T5, how different are their output parameters? So how does it vary?
Oh, it varies a lot. I think Flan T5, because of the fact that it was instruction tuned and it had this further reinforcement learning. I mean, they have a policy network on what to say. Even on tasks that T5 has been trained on, Flan T5 produces much better output, actually, which is very weird, but yeah, it is what it is. Yes, please.
And have you done any testing for like switching from Plan T5 to Llama, or is that just early stage?
I mean, not to Llama, but Meta just released a model called Seamless M4T, actually, like 3-4 days back. We are looking to move on from Flan T5 to Seamless M4T, both for Whisper and Flan T5. So we'll end up using just Seamless M4T for this. Yeah, fingers crossed. I still haven't used it. I just, yeah, just testing.
Any other questions?
All right, perfect. Thank you.